Welcome back. This video is going to cover the topic of smoothing for regression problems. Now, I think this is a very important lecture because I view it as the gateway to a very large class of problems called non-parametric regression methods. And so these non-parametric regression methods are really the heart of machine learning. So what makes it non-parametric? Well, let me review what we've been doing. Okay, so what we've been doing is we've been using what I could call parametric regression. So I have some x and I have some y, and maybe I have a scatter plot like this, and I say, aha, that looks like a linear relationship, so I will fit a line. So I would assume a parametric functional form for the relationship between x and y that would look something like this. Y is equal to beta naught plus beta 1 times x plus some errors. And what's really important is that this relationship is a function of a small number of unknown parameters. In this case, my intercept and my slope and the variance of these errors. Or maybe I observe a scatter plot that looks something like this, and I say, aha, I see diminishing returns. I bet a square root might be exactly what I need here. So maybe I take a transformation of x, and I say, well, y is equal to some intercept, so I'll give myself a little offset here, plus beta 1 times the square root of x, and then I've got my errors. All right, so again, I have a functional representation of this involving just a small number of parameters that I can go estimate with least squares. That's parametric regression. What is non-parametric regression? Well, that's what we're going to do today. And so what non-parametric regression is going to do is it's going to automatically detect that there's a curve here and find that. Or it would automatically detect that this is a line. All right, so I don't have a simple equation like this involving a few parameters. It's a very flexible function that's capable of detecting any relationship. I mean, it could be a very weird relationship that's like this, and my non-parametric method would automatically detect, I think the real relationship looks like this. All right, so that's our goal. I like to call this the Holy Grail. Okay, so the Holy Grail would be where I can just give my machine learning method some data, and it will learn, or it will adapt and discover any relationship that's in my data. And so that's the Holy Grail. I'd like to just mention some of the history on this. So for machine learning is such a hot area right now, but it's actually been for the past 50 years, people have been working on trying to achieve this, where they can just put the data in, push a button, let the machine grind away, and detect that relationship. So we're going to cover a lot of different attempts to get at this Holy Grail. I think probably the closest to it is maybe random forests. It's one of the most automatic methods around for automatically detecting this. But there's many others: support vector machines, neural networks, and the smoothers that we're going to be covering today. All right, so let me kind of describe the model as well as how these methods work at a high level. So here's my model. I'm going to assume that my y's have been generated as follows. So every y is a function of some x plus some noise. And I'm going to assume that the noise has mean 0 And we'll make an assumption that the noise has a constant variance sigma squared. So we'll continue to assume homoscedasticity. And so let me just draw a little picture of what I have in mind here. So if we're going to generate data from this model, I need an f. So let's just say here is my f. And so let's give ourselves a bit of nonlinearity, make this a little bit interesting. And so this is my true f. So let's just write true f at x. But that's not my data. The data is going to be, for every x, I put it into this function, and then I add some random error to it. Now, I haven't assumed normality, but it's certainly nice if we have normal errors, but not necessary. Okay, so, let's say I've got an x here. Here's my f at x. Give myself some error. Here's another x. Okay, my error is going to be down here. And so maybe my data looks something like this. Keep your errors about constant spread. And so what I have in mind here is I have a, let's say a normal distribution. If we assume normality, what's important about this is the mean of this distribution is the curve. So the errors have mean 0, meaning some of them go above, some of them go below, but the center of this is the curve f. And I've tried to rig it so that the spread is constant. Boy, that's not a very good looking normal curve, but let me redraw that to make it a little bit better. So this has variance sigma squared, this is variance sigma squared. All right, now, how does a smoother work? Without giving you any equations, I want to give you some intuition. So most of these non-parametric regression methods are going to have what you can think of as a dial, okay? A little knob that you can turn, and on one extreme, so if you turn the dial all the way to the left, you end up with a flat line. If you turn the dial all the way to the right, you end up with a with something that wiggles too much, and somewhere in the middle, when you turn the dial somewhere in the middle, it's going to be just right. So let me just sketch this out for you. So if I turn my dial all the way to the left, I'm going to get a function that is way too rigid. So this would be, actually the value there would be y bar. That's the intercept model. And this would be, you can think of 1 degree of freedom. I've given it, just the intercept, go estimate that and be done. Well, I could give myself a little bit more, flexibility if I turn the dial a little bit to the right, and we often measure the amount that we've turned the dial by degrees of freedom. And so this would be 2 degrees of freedom, and I've assumed a line. And so notice this this line is too rigid also. We're not quite capturing the curvature. Now, let's just say I turn the dial all the way to the right. And in that case, what I would end up with is something that really wiggles a lot. All right, so I'm trying to hit every one of these points. I guess I'm not going to quite hit that one. And this would be large. Maybe I should say very large degrees of freedom. And clearly I've overfit the data. So what I mean by overfitting is if I generated a big test set from the same model, so just generate 10,000 data points from this model, none of these models, the red marker, the orange marker, or the red pen, none of these models are going to do very well on the test set. And so what I'm really sketching out here, what I'm really thinking about is the bias-variance trade-off. So let's say this is my error. And remember, we had this graph that looked something like this. This is my training error. And so the training error, if I start out with this red line, the training error is horrible. If I go to the orange line, the training error is a little bit better. If I go, okay, I turn my dial all the way to the right, and I get that red pen, my training error is close to 0. But you know, we're going to see on the test that that doesn't work out very well. So this is complexity, the complexity of my model. This is high complexity. This is low complexity. Now, if I have that test set with you know, 10,000 data points, what we're going to see is that here's your test set error. So here's the test set. And so up here, that's the red line, the red marker. Here's your orange marker. Here is your red pen fit, the one that wiggles all over the place, where my test training set error is great, but my test set error stinks. And what I'm really trying to do is get about here. And so this is the best complexity. So that's the goal. And so what I really want to get is some data set. Let's see, I'm running out of colors here, but maybe I have a black fit here that captures the signal. So think of this as the signal and separates it from the noise. All right, so this is what's really happening down to, well, there's these stochastic variations around the line. All right, so that's the whole idea. And what we're going to be doing is proposing a lot of different ways to represent such a function. You know, so how do I get a function that's capable of adapting like this? And so that's going to be the name of the game as we go forward. So this slide outlines some ways of doing this. All right, so I'm going to lay out the assumptions a little more formally here. So this is what I wrote on the piece of paper earlier. I'm going to assume that I have n observations, and for the sake of describing some of these, I'm going to assume my x's have been ordered. So x1 is going to be the smallest x, and xn will be the largest x. I've also assumed that I don't have repeated observations, so like I don't have multiple x's taking the same value. So these are all strictly, you know, greater thans. You know, smoothers will work without that assumption, but when I'm defining some of these smoothers, it's going to make it a little bit easier if I can assume that these are distinct x's. All right. So one of the oldest approaches is something called a Binsmoother. Binsmoothers have another name, which is the regressogram. So this is a very old name. I believe it goes back to the 1920s. Regressogram is a play on histogram. So what's a histogram? Well, histogram finds bins. It counts the number of observations in each bin, and then it creates bars that have an area proportional to the number of observations in the bin. So that's how a histogram works. So a regressogram is just like a histogram, where I make some bins. So I'm going to take I'm trying to approximate this function over some interval, call it a to b, and I'm going to divide it up into k bins. Instead of just counting the observations, all I'm going to do is compute the average of y in each bin, and that's going to be my estimate. So let's just go off. There's too much stuff on my plot there. I'm going to redraw this. So here's x, here's y, and I'm going to redraw my scatter plot to try to do the same thing. Give yourself a little bit of curvature. And so here's the whole idea of a Binsmoother. It's extremely simple. In terms of my notation, this is A, and this is B, and I got all those x's that are distinct values. And so all I'm going to do is divide this up into some bins. How about 3 bins? So those are my 3 bins. And what do we do next? So that's step one of this bin smoother. Step two is your estimate of f is going to be the average of the y values. So I have to find the average of all these y values, and I think it's going to be about here. Then I have to find the average of all the y values here, and I think it's about that value. And then I'm going to take the average of all these values, and that's going to be my function estimate. So the notation that I'm going to use is this is going to be f hat at x. So that's my estimated function, whereas the true function that I don't know is this. This is the true f. Right, so this is approximating that. Now, I want to just talk you through a couple things here. Number one, if I had a lot of data, so let's say I had 1 million data points. Okay, so if I had 1 million data points, then I could have a whole lot of bins. So maybe I give myself 1,000 bins. So I have 1,000 bins. And so what I hope you would see is that if I had 1,000 bins, okay, this function would really, so each one of these, what I have here is a step function. It's called a step function. But with 1,000 bins, my step function would start to hug the true f. And if I went to 2,000 bins, it would get even closer. All right, if I had 3,000 bins, it would get even closer still. So if I had a ton of data and I gave myself a lot of bins, what I would hope you'd see is that this step function would converge to this true f. All right, and lo and behold, I would have my magic estimator that would approximate that f very well. All right, now one other thing I'd like to point out is that I did something kind of simple, and I took my interval and I roughly divided it into thirds. So maybe I had a third of my data in each of those places, or I took the interval A to B and I just chopped that into thirds so that this segment is equal to that segment is equal to that segment. But it seems like a natural thing to do, but it's not particularly smart. Not particularly smart because the function is very flat out here. I don't need a lot of bins to describe the nonlinearity here because there isn't much nonlinearity. On the other hand, actually it's not nonlinearity, it's just slope. There is no slope here, where off in this region, I really need more bins. This is where I need the bins. All right, so this whole idea of just, chopping it at the tri-tiles or just chopping the x interval up into thirds is not particularly smart because I want to have more bins where I need them. I need it where the function is changing a lot, where there's slope. I don't need a lot of bins up here. So what we're going to see when we get to trees is that there is an adaptive method of choosing where these bins are that will only give us bins where we need them. All right, that's the idea of a bin smoother. So just a couple quick examples here. Number one, we have this art museum problem where I had a survey and we asked people, what is your age? So they reported their ages in these buckets on my survey. So we had a bucket 10 to 20, 20 to 24, 25 to 29, very common to have such buckets on a survey. Then we asked, how many times have you been to an art museum in the past year? And so that is going to be 0, 1. Did you visit an art museum in the previous year? So I have the number of people in each bin and the number of visitors. If I take the number of visitors divided by the number of people in the bin, I get Y bar, which is really the percentage of people who've been to the art museum. So what you'll see is that we can plot this y bar as a function of my my bin, and you get this black step function. And what you should note about this black step function is it's extremely wiggly. Okay, so note if you're under 20, there's a high chance you went to an art museum, then it drops a lot, then it goes up, then it goes down, then it goes up, then it goes up a bit more, then it drops, then it goes up and down. And this is just way too wiggly. Now, I've computed the standard error. So the standard error, let me just refresh your memory. This is basically a binomial. So if we have, let p hat equal the number who go over the number in the bin. That's number in the bin. You can say the if you want, in the bin. All right, so that's just an estimated proportion. The standard error of a proportion is this: p hat times 1 minus p hat over n. So what I want you to note is that there is an n in the denominator. So this is something you should have learned in your basic stats class. When you have a larger sample size, the reliability as measured by the standard error increases. When you have small n, the standard error gets very wide. Okay, so that's, remember, a confidence interval for this would be p plus or minus 1.96 times the standard error. All right, so your error bars get wider when you have small n than when you have large n. And if I have, a sample of 1 million in each bin, then this thing is going to be practically 0, and my estimate is going to be perfectly reliable. So the point I'm trying to make here is that I have a very high variance estimate because my sample sizes just aren't that big, and because I have such a big standard error, if I were to superimpose confidence intervals around this, they would be very wide. And basically, I'm following noise because my sample sizes are so small. So what do? Well, we have to turn our dial. Remember, we have this magic dial. So the way the dial works for a bin smoother is just reduce the number of bins. So off to the right, I cut my bins in half. Instead of having 12 bins, now I have 6 bins, and I have a new average. So where is this stuff coming from? Well, let's just, if I add up these 3 values, I get 370 cases. If I add up these values, I can almost do that in my head. It's like 136 divided by 370 gives me this mean. And what I want you to note is now the standard error has dropped a lot. Okay, so my estimate is going to be more reliable. I've reduced the variance of my estimate. The red dashed line shows the estimate for this 6 bin smoother. So the red line is showing that. And what you'll see is that we've gotten rid of a lot of the wiggles. So if you're very young, you tend to go to art museums a bit more. I like to speculate that this is because you don't have kids. And then what happens is you get married and you have kids and you don't have time to go to an art museum. You go to the dinosaur museum instead. Then when the kids get old enough, well, then you can start going to art museums again. But then at some point you get too old to deal with all the fuss. Like when you're 70 plus, maybe you don't want to deal with going into the city. This is in Chicago, by the way. And so the probability drops. But I find this is I can almost approximate a nice smooth function here with fewer bins. Okay, so that's the idea of a bin smoother. I'm going to give you one more example, and that is the example of a sine wave. So I want to have a true function that has some nonlinearity, but I want to know what the true function is so that I can generate giant test sets. So what I'm going to do is just generate, say, 3/4 of a cycle from a sine wave. And then I'm going to give myself some errors where I actually know how much error I give. So the amount of error is 0.0625. That's going to be the true mean squared error that we're going to try to achieve with our smoothers. And so here's my function. And I'm going to make this problem very difficult for myself in that I'm only going to have 30 data points. So if I gave myself 1,000,000 data points, this problem would be dead easy because I could then just give myself 1,000 bins and my approximation of the sine wave would be perfect. But when I only give myself 30 data points, I've made a very difficult problem for myself because I can't have that many bins. So how do I do this with a bin smoother? Well, I decided to just chop it up into 3 bins. So I made a bin at 1 and a bin at 2. And so I put this into a linear regression model. The way I made these bins is with the cut function. So what this cut function does is it says I want to have cuts at 0, 1, 2, and 3. That's what the 0:3 means. Is I want to break point here, and so you can see that corresponds with this break, and then also here. If I use a linear regression, that will find the mean of that, and so what we see up here is exactly what the linear regression is showing. So the height of this bar would be the intercept, which would be 0.63. The interpretation of this bin from 1 to 2 is this step goes up by 0.06. So the height of this line is really 0.63, the intercept, plus 0.06. So that's going to be at about 0.69. Then what is the height of this step? Well, it's going to be 1.42 less than the intercept. So it would be the intercept minus 1.42, which is about, what is that, minus 0.8 or so. And that would be the height of this. And so that's my function. You should say, that doesn't look very good. And you're right. So it's very steppy, if that's an adjective. So it's very rigid. Clearly, I need more bins to make this approximation work. So in the upcoming videos, I'm going to show you some ways to improve this function with this tiny data set. So we're going to get smarter about this and see how a spline will do the trick. Before we do that, though, let me just jump over to R for a second, and I want to show you the data set. So when I use that cut function, so when I said I want to make a new variable called bin, and I put this into this cut function, what it does is it creates this additional variable called bin, and bin is a factor, and this is interval notation. So what this means is all values greater than 1 and less than or equal to 2. So the round bracket means strictly greater than. The square bracket means less than or equal to. And so what this is really saying is the x value, 1.68, is somewhere between 1 and 2. The x value, 2 point something or other, is somewhere between 2 and 3. And the x value, 0.089, is somewhere between 0 and 1. So that's how the cut function works in R. Now, let's go back to the course packet for just a second. And the next question is, how many bins do I need? So if I have too many bins, I'm going to follow the noise in the data. And if I have too few bins, the function is going to be too rigid and not capture the nonlinearities. So the way to handle this is we could have a test set. So notice what I've done here. I've generated myself a massive test set with 10,000 observations from exactly the same function. Then I wrote a function here that will accept different numbers of bins. So I can pass to it the number of bins that I want to make, and I pass to it the bins that I want to make, and then it will create the necessary bin variable for me, fit the model, and evaluate how well it does on both the training and the test set. And so I tried this for anywhere from 1 to 30 bins, and I tried to choose mostly multiples, numbers that divide 30, since I only have 30 data points. So this is, if I had 30 bins, notice my training mean squared error is exactly 0, and my test set mean squared error in the 10,000 observations is very bad. And so I'm plotting this off to the right, and this is really the first time we're seeing this bias-variance trade-off from an actual data set. Okay, so this is the complexity of our model. We have a very complex model with 30 degrees of freedom. My test set error is horrible. My training error is perfect. Now, if I cut that in half, so if I have 2 observations per bin, now my sample size per bin then is 2, you're going to notice your training error increases a little bit. The test error drops substantially, and that's that point. Okay, but notice this curve is still, well, going down if I go to the left, meaning 15 bins is still too complex. So let's reduce it further. So 10 is the next number that divides 30 evenly, and you'll see our training error has dropped. Our training error has increased a bit. It's kind of doubled in size, but the test error has actually gotten better. So we've gone from this triangle to this next triangle, which is a bit lower with 10 bins. Then I just tried 1 through 9 bins. If you have 1 bin, you're going to see both your training and your test set error are horrible. We go to 2 bins, things get much better. 3 bins, better, but not quite as much. 4 bins, it looks like the red line is still improving a bit. And so to choose the number of bins, we'd want to find the bottom of this, which I think is somewhere around, looks like 7 or 8. You don't always want to go all the way to the end. So I would pick somewhere in the 7 or 8 range. When I look at the actual numbers here, it looks like 7 is the optimal number according to that. All right, so when I covered this slide, I actually skipped over running means and nearest neighbors as well as kernel smoothers, but I'm going to cover that in another video. So I'll see you in a minute. Go take a break and come back and watch my nearest neighbor video.